All right, the second day of Unit 8 is going to be all about exponential functions. Over here on this graph, I have just kind of your most basic exponential function. If you notice, it starts out super flat and then slowly increases until it really takes off. Over here, there's two equations that you will mainly see when it comes to exponential functions. The first one is your most basic equation. And we just need to know what all the different letters stand for. Of course, f of x always stands for function. A is, it's kind of like your y-intercept. It lets you know what your starting value is. So this is your starting point. It's also known as your initial value. B is what we refer to as the base because it's what holds your exponent. And your exponent over here is your variable. So what sets exponential functions apart from other functions is that your variable is actually in the exponent. So every time we use this, there should be a number plugged in for a and b, and we'll still have that exponent as a variable. Down below is another function, or sorry, another equation, and this one is very similar. We'll use this equation when we're talking about rates or percentages. So we will get to word problems today, and all of our word problems are mainly going to be based off of this equation here. The great thing about this equation is that A still stands for your intercept or your starting point. Especially in word problems, I want you to think initial value. So anything where you say you're starting with, or you're investing this much, or you have this much money, or whatever it is, that's your A value. 1 just stays as 1. Plus or minus, this is where we have to decide, are we increasing or are we decreasing? So if you're increasing so much money each month, well, then we're going to use a plus sign. If you're decreasing or losing value, then you're going to be subtracting. R is our rate, and that's usually presented to us as a percentage. Remember, if I'm going to use a percentage, you just take whatever the percentage is, and you're going to move the decimal 2 places. And that's how you're going to plug it into the equation. And then lastly, my variable is this t up here. And they use t because more times than not, it's always going to represent time. So there's your 2 equations we're going to be using today. Hopefully you can read that and mark all that down. Our first example is just looking at deciding whether this is an exponential growth or an exponential decay function. On the first page, we saw an exponential growth function because it went like this. So it's a growth because it's growing over time. Exponential decay is a function that's going to decrease over time. So the way I tell whether something's going to be growth or decay is I look at the b value. Here, b is 3/4. Since 3/4 is less than 1, this tells me that this is a decay function. So if your base of your exponent is less than 1, so a fraction, it will be decay. If it is 1 or greater, it is going to be growth. Now it says to make a t-chart or a table to sketch the graph. I'm going to help you guys make a t-chart, but we all know how well graphing works here. So you guys can just sketch your own graph, or if this is something we need to go over in class, just let me know. Whenever I tell you guys to make your own table, your own t-chart, it's best to just go from -2 up to 2. So again, I'm going to type 10 times 3/4 to the x power in my calculator, but in place of x, I'm going to put -2, -1, 0, 1, and 2. So when I type -2 into the equation, I get 17.7 repeated. If I put -1 as my exponent in place of x, I get 13.33 repeated. If I put 0, I get 10, and we should know that because remember this a is our starting value. It's our y-intercept. So when x is 0, my y value is 10. For 1, if I put 1 as my exponent, I get 7.5. And when 2 is my exponent, I get 5.625. This chart or this table right here proves that this is exponential decay because notice that as my x values get bigger, my y values or my outputs actually get smaller. Now when you go to graph this, you just need to make kind of like a little upside down T like that just to represent -1, 0, 1, 2, just to represent the 5 inputs that we had. And then you just need to graph your outputs. It needs to go from 0 all the way up to 17.7. So you can count up this line however you like. So I think if I count by threes, so when my x value is -2, my y value is up here at 17.7, so just below 18. At -1, I was at 13.3, so just above 12. I'm at 0, 10, so it'll go just above 9. 1 was at 7.5, so it'll be about halfway between 6 and 9. And then 2 is at 5.625, so just below 6. So notice the gap in between each of my points going down is getting smaller and smaller. So all of our graphs should have that kind of like J shape. So this is your first try on your own. This is the function I gave you. First, decide whether it's growth or decay. Make a t-chart going from -2 to +2, and then just a quick rough sketch of that graph. I told you we're going to get into word problems. This is example 3. This word problem is over rates. So remember, when we were talking about rates, we're going to be using this equation, where I have a parentheses 1 plus or minus r to the t power. So I'm going to read through this and pick out my important information. The first thing I want to look at is they should give me a question somewhere. They want to use a t-chart to predict when the population will reach 20,000. When the population, that tells me the time. So that's my variable. That's what I'm looking for. So in 1981, the Australian humpback whale population has 350 and has increased at a rate of about 14% each year since then. Write a function to model the population growth. So first thing I notice is that I started with 350 humpback whales. So that's going to be A. They give me 14%. So my rate, remember if we move the decimal 2 places, it'll be 0.14. So that's going to be what I put into my actual equation. Because I'm increasing, remember I have to decide whether to do 1 plus my rate or 1 minus my rate. Since I'm increasing, I'm going to do 1 plus r. So I'm going to take all, and then it wants to know when it will reach 20,000, when the population will. So this is f of t. They want to know when will my output be 20,000 whales. So when I first write my equation, I'm going to say f of t equals, my a value is 350, then I have 1 plus 0.14, and I'm trying to figure out how long, so t is my variable. Here they're wanting us to predict when the population will reach 20,000 humpback whales. Kind of just like the P over Q, there's not a really good way to figure this out. What you're going to do is you're just going to make a table. So my time and the number of whales. And you're just going to pick a number and plug it in and see how close to that 20,000 you get. So if I start with 10, if I plug 10 into my equation, so I do 350 parentheses 1 plus 0.14 raised to the power of 10, my answer would be 1,298 whales. That's not quite close enough. I needed to get 20,000. But remember, exponentials start pretty slow and then take off. So I'm going to try 20. just see what happens when I take a 10-year jump. When I plug 20 into this equation, I only get to 4,810. So we're going to keep going and see where I get at 30. When I plug 30 into my equation, I got 17,833 whales. So this was super close because I need to get to 20,000. So from here, I'm not going to increase by tens anymore. I'm going to see where 31 years get me. So when I plug 31 into my equation for t, my answer is 20,329. This does get me to my above 20,000 population. So this is actually going to be my answer. And I'm confident in saying 31 is my answer because after 30 years, it didn't quite get to 20,000. So you really want to make sure that you find the numbers on both sides of your goal. So when it says predict about which year, so it'll be after 30 years, after 31 years. So you can say after 31 years, or you could even give them what year that would be. If they started in 1981, 31 years after that will actually be 2012, so just a couple years ago. So your try on your own is very similar. Read through the problem, figure out what your starting value is, whether you're increasing or decreasing, and your rate, and then use that T-chart to predict when you will drop below 8,000 people.